Hello everyone, welcome back to our Step 2 Engineer channel. So in our video, we explain how the MAWP value of the shell body, which is a major component of the pressure vessel, is calculated. We also covered how PV Elite determines this value and which ASM code and formula are used for the calculation in detail. So in today's part 2 of the video, we'll be looking at the major components of a pressure vessel, such as the shell and heads, as well as the minor components like nozzles and boot heads. These major, minor, and individual components will have varying MAWP values depending on factors such as their usage conditions, rating, and thickness. So if the MAWP value for a major component is determined this way, then how should we verify it for minor components like standard flanges? Where should we check the values? How can we review them? And how should we cross-check the data? Additionally, the different MAWP values obtained from major and minor components contribute to determining the governing MAWP value or, in some cases, the overall MAWP value for the entire vessel. Finally, the officially declared vessel MAWP value must be specified on the GIA drawings. In this video, we will explain in detail how to verify and calculate these values, and how to officially declare the final MAWP value for the vessel. So, just like in the previous video, we will refer to the relevant codes, references, and documents to provide a clear explanation. These details are important for understanding, so please continue reviewing our presentation slides. Great! Let's continue by reviewing the presentation slide. Feel free to guide me through the content if you'd like me to help explain any part of it. So the first data on this slide is taken from the design data of the pressure vessel, which we discussed earlier, focusing on the MAWP of the major body, the shell. The reason for this is that since the vessel design data and size are the same, it makes the study a bit easier and more straightforward to follow. So as mentioned earlier, we have the same design pressure and temperature conditions, a pressure of 10 bars, a temperature of 120 degrees Celsius, and an MDMT of -40 degrees Celsius. Now, since I'm about to talk about the MAWP of the minor component, the nozzles, I've highlighted the nozzle material here. So for the nozzle, if we have weld neck flanges, there will be two parts, the nozzle neck and the nozzle flanges. The nozzle neck will use pipe material as a 333 grade 6, as it's a pipe, and the flanges will be forged flanges made of as a 350 grade, LF2, as is commonly known. Additionally, I'd like to point out that the two materials, SA333 and SA350, are not typically used for normal temperature conditions. These materials are intended for specific purposes as set by the client, and they are not the usual choice for standard temperature conditions. What I mean is that these are low-temperature carbon steels, which are used in very low temperatures, often well below freezing, to handle the extreme low temperatures. So to clarify, SA333 is a low-temperature pipe material, and SA350 is a low-temperature forging material. Alright, let's move on to the next page. What we're looking at right now is the list of nozzles on this vessel. This list is based on the client's requirements, and the nozzle sizes and ratings are provided according to the specific service conditions they need. So in this section, we can see that there are both 150-pound and 300-pound flanges listed. So there are quite a few nozzles, but to make it clearer and more distinct, I'll simplify the model by focusing on two types of nozzles. I'll continue explaining further from here. So one of the nozzles is in 1, which has a 30-inch size and a 150-pound rating. The other is K5 with a 2-inch size and a 300-pound rating. So I'll simplify these two types as a model and then continue explaining from there. So what we're seeing now is that the N1 nozzle has a 30-inch size. The nozzle material is as a 350LF2, and the flange material is also as a 350LF2. Here, What I want to add is that both the nozzle neck material and the nozzle flange material are SA350LF to forged materials. The reason for this is that, based on the client's request and availability in the market, we opted for materials that are easy to source. Instead of using pipe and weld neck flanges, we used long weld necks, which are integral forged components. This is why both the flange material and nozzle material are SA350LF2, a low-temperature carbon steel forged material. So to clarify, the carbon steel with a 150-pound rating falls under the grade class group of 1.1 or below. So at that point, the MAWP of the flange, based on this rating, material, and group, will be 66.9 for bars. Now, let's move on to the next nozzle. This nozzle is K5 with a 2-inch size. As mentioned earlier, the materials and grades are the same, but the flange rating is 300 pounds. So to put it directly, the 150-pound rating is already more than enough. Why? Because our required design pressure is only 10 bars. So since the MAWP already exceeds 10 bars with the 150-pound rating, so why don't we use just 150 pound? Did we use a 300-pound flange here? Simply put, it's because the client specified it based on their piping design. This could be due to the instruments that will be installed on this nozzle, such as pressure gauges, pressure transmitters, sensors, level gauges, or level transmitters. Based on their P&ID and line design requirements, they specifically requested a 300-pound flange for this location. Therefore, even though 150 pounds would have been sufficient, we used 300 pounds as per their requirement. So since this is a 300-pound flange, its MAWP has significantly increased to 46 bars. This is the information we can see when we input the N1 and K5 nozzles into the PV Elite model. So in this slide, what we can see at the top left corner is the ASMEB 16.5 specification for flanges. This is extracted directly from ASMEB 16.5, which provides the standard specifications for flanges. What this section represents is the maximum allowable working pressure MAWP of the flange, which depends on its material group and the design temperature we are using. Simply put, what we see here is a table listing how much pressure this flange can withstand at different temperature ratings. So since this unit's vessel uses SA350, it falls under group 1.1. So if the material is different, it will fall under a different group. So this means that based on the group and material, we need to check and verify the corresponding tables accordingly. This is just a simple selection based on basic carbon steel. So SA350LF2, as we can see here, falls under group 1.1. Now, our design pressure is between 100 and 150 bars at 120 degrees Celsius. So at 150 pounds, the flange's MAWP will range between 17.7 and 15.8 bars. For a 300-pound flange, the MAWP will range between 46.6 and 45.1 bars. So if we look at the image on the right, we can see the values we get from the table for 100 and 150 bars. However, what we need is the MAWP for 120 degrees Celsius. To find that, we use linear interpolation, which is what we can see here. So for the 150-pound flange at 120 degrees Celsius, the MAWP is 16.9 for bars, and for the 300-pound flange at 120 degrees Celsius, the MAWP is 46 bars. What we're doing here is verifying the values given by the program and cross-checking them with the code to ensure their accuracy. We need to check if the values from the model align with the code's specifications. To do this, we look at the relevant areas in the code to confirm the calculations. I'll explain this process in detail when I go over it again. So the nozzle flange MAWP results shown in the image at the bottom left are the values generated by the PV Elite model after we modeled the nozzles. When we generated the report, these are the values that came out. So the values we saw earlier in the slide were the ones we observed after keying them into the model. Now, we need to cross-check these results with the specifications and the code to verify their accuracy. Once this is done, we'll prepare the final calculation report to submit to the client. Exactly. When submitting the report, we must double-check to make sure the values generated by the as mentioned. We need to verify that the values generated in the report are indeed accurate by cross-checking them with the specifications and the code before finalizing the report for submission. So when cross-checking the report, for the in-one flange rating operation connection, we should confirm that the operation design connection for the 150-pound flange is 16.9 for bars, and for the 300-pound flange, it should be 46 bar, ensuring both values are correct. So up to this point, we are focusing on the minor component, the nozzle. There are actually many nozzles, but to avoid overwhelming with too much detail, I've simplified it by focusing on just two nozzles. So one nozzle has a MAWP of 16.9 for bars, and the other nozzle has a MAWP of 46 bars. These are the MAWP values obtained from the minor components. So the entire vessel consists of major components like the head and shell, as well as minor components like the nozzles. So by combining all the components, both major and minor, we can determine the final MAWP maximum allowable working pressure of the entire vessel. This overall or governing MAWP depends on which component limits the pressure, and will decide that based on the specific component's strength and design. Let's move on to the next slide to continue the explanation. So the images above show the MAWP values of the major components. So for the pressure vessel on the left side, we have cap 1 on the right side, cap 2, and in the middle, we have the shell. The MAWP of cap1 is 15 bars, and the MAWP of the shell is 19.85 bars. So cap 1 and cap2 are identical because both ends of the vessel are designed the same way. This is why they have the same MAWP values. As for the minor components, the MAWP of nozzle N1 is 16.9 for bars, and for nozzle K5, which is a 300-pound size, the MAWP is 46 bars. So when we compare all the minor and major components, it's clear that the MAWP, which stands for maximum allowable working pressure, represents the highest pressure the system can withstand. Therefore, we should always consider the lowest governing value as the final pressure value. For example, if we mistakenly set the value to 16.9 for or failed to carefully review the report and incorrectly marked it on the drawing or the flange, then if the vessel actually reaches 16 bars, the cap area, which is only designed to withstand 15 bars, could potentially fail. This could lead to a serious issue in the cap area of the vessel. So based on what we are seeing now, depending on the minor and major components, we have taken the minimum value of 15 bars, which is the limit for the cap. Technically, we can say that the MAWP of this vessel is governed by the cap, as it is limited by the cap's maximum allowable working pressure 15 bars. Therefore, technically speaking, the MAWP of this vessel is governed by the cap, limited by the cap. So to summarize, the simple model we have presented shows that the design pressure is 10 bars. However, based on the chosen thickness and the ratings of the flanges used, the overall MAWP of the vessel is 15 bars. So by watching the first video and then the second video explaining the minor and major components, you will clearly understand how to evaluate the MAWP of the pressure vessel, including the major and minor components, and how to determine the final MAWP. So thank you to Step 2 Engineer channel for watching everything until the end.